Okay, hello everyone. Can we start? What do you mean no? Sure. We are going to start. Did you guys miss me? Probably not, right? But that's okay. I saw that last Wednesday Dr. Diaz let you off easy by stopping after an hour. At least there's only 1 hour video. So nobody complained, right? You should. Or was it 90 minutes and 30 minutes are missing from the video? I looked at the lecture last Wednesday. It was only 60 minutes. But he covered a lot more than I would be able to do in 90 minutes, so that's good. And then on Friday, this was 45 minutes, and I saw that he left off with enolates as nucleophiles. And I would just like to make one last point there where he basically stopped. So this touches on something which we will discuss in much greater detail when we go to carbonyl compounds. But nevertheless, in the context of nucleophilic substitutions, it's of course important to realize that also enolates are important C nucleophiles, which upon a base you are forming such an enolate where you can draw mesomeric structure like this. The more important mesomeric structure certainly is the one which is drawn like here, where we localize the negative charge on the more electronegative oxygen atom. I would also like to encourage you at this point that you try to learn simply to, when you then discuss reactions or write a reaction mechanism, that you are able to do this from this structure. I know many of you like to, they draw the enolate structure and they say, okay, now I do the reaction, I draw this one, and then I do the nucleophilic substitution. This is of course all correct, but this is the more accepted way to look upon this for an enolate. And so typically bases can be lithium bases, LDA. We go into elimination also this hour here. So LDA is the diisopropylamine lithium compound here. This is basically the equivalent for this anion here, and so that is a very strong base, and it's a very strong base, but not a nucleophile, because this is sterically bulky. It will not attack the carbonyl group in an addition, but it will rather undergo, it will rather attack the outside to do in deprotonation here. And so in principle, if we write this absolutely correctly, you should always keep in mind that there is a counter anion here as well. So now that I have put on this here, it's not really any longer a resonance structure here. If we have the lithium compound here as well, because also keep in mind the definition for mesomeric structure is this movement of electrons and not movement of atoms. So by writing here the counter cation in this as well, I formally have not, I'm formally not writing mesomeric structures any longer. And so enolates are very good nucleophiles, and they are nucleophilic both on 2 points, and that is where Dr. Diaz started or left you off. So this is obviously a nucleophilic position, and this is a nucleophilic position as well. And the question is, when it reacts with electrophiles, where will it react? And it's again a soft and hard base argument you can bring here. The oxygen as the more electronegative, less polarized atom is considered a hard center. This is considered a soft center. And with soft electrophiles, reactions typically will occur on the carbon center. With hard electrophiles, they will occur on the oxygen center. And one interesting example I would like to show you to this effect is that we consider an alkylation. So here we have typically if we have a look at methyl iodide, we have a very soft leaving group. So typically we would consider this here as a soft reagent as well. And so therefore, alkylation indeed will take place on the carbon. The reason I show this to you is that the very same electrophile, which is the methyl group here, can also act, if it has a harder leaving group, can also act as a hard electrophile. And so very famous type of salt are such trimethyl oxonium salts. So it's basically dimethyl ether which is alkylated by a methyl group. I show you how this is being made in a moment. This has a name. It's the so-called Meerwein salt. Meerwein, a famous chemist at the University of Marburg. If you are in Marburg, there are Meerwein streets, and so he was a professor there, and this was one of his inventions. Wagner-Meerwein rearrangement is another one where you might have heard the name of Meerwein. And so this really is a hard reagent, and what this then does is that the nucleophilic substitution will really take place on oxygen. So again, from my point of view, this is a pretty amazing argument, and also good argument for this soft and hard concept, that the same type of reagent, we are transferring the same group, you can switch the reactivity by adjusting the leaving group here. Here we have a very hard leaving group, so this becomes a very ionic type of methyl plus here, which will react on the hard center. Here we have an overall highly polarizable molecule, soft leaving group, and so attack will take place on carbon. The Meerwein salt can be quite easily synthesized by reacting methyl iodide with dimethyl ether. Do you think this is a good reaction per se? If you bring these two together, nothing will happen. In principle, what you are trying to do here, of course, again, is a nucleophilic substitution between methyl iodide and this ether compound here. But here again, we would have a more hard center, we would have a softer center here. The reactivity does not really match, and it's not sufficient just to bring these two together to form such a salt. However, what you have to do is you do this in the presence of silver tetrafluoroborate, and then you make use of the high affinity between silver and iodine. Let me bring, so that we are not having too many equations, let me write this here again. So we are reacting this in the presence of silver tetrafluoroborate, and then the high affinity of silver to combine with halides to form insoluble silver iodide. Makes this then as a very hard metal plus center. And so with this, then the nucleophilic substitution is successful, and you are able to make this type of salt, which then of course has the leaving group attached to this here. It's all a very useful reagent because in many cases you are interested in enolates to do an O alkylation rather than a C alkylation. On the other hand, you can also see expensive, relatively expensive thing, because you need stoichiometric amounts of silver salts here in order to make this reagent. And so it's not the most readily available and most expensive reagent to make here. So again, we will look into enolates a lot more when we talk about carbonyls, but again, take this as an example of an important application of the soft-hard acid-base concept. And basically, you can see here the fine-tuning which is possible, which can then determine different reactivity. Okay, so now I hope that you already know everything on substitution reactions. I would now like to start on eliminations, and then we will go back because we will see in one type of elimination that this is closely related to substitution reactions. We will go back a little bit to substitutions and do some more comparisons here. So let's turn over a new leaf here, eliminations, elimination. And so what we are going to cover are eliminations which can be either 1-1, 1-2, and 1-3 eliminations. These are the three aspects I want to cover. And by far, the most common and most readily or most useful eliminations are the so-called 1-2 eliminations, where you are going through a process of eliminating from adjacent groups, from two adjacent carbon two groups. Usually, or most commonly, you have a good leaving group like a halide and a proton. So this is the typical base-mediated process. But the other principal process also often seen is that you can actually have a group which has two leaving groups. And so most commonly here, in both cases, are halides. But we will also see other leaving groups as well, like special leaving groups which have oxygen leaving groups. And here in this case, this is most of the time, really here most of the time, it's halides. There are very few other examples known where you can eliminate two groups from here. And here, rather than a base, which we use here because we are eliminating HX, in this case, we would like to eliminate X2. And so for this, you usually need a metal very commonly used, for example, is zinc, which then gives you the same product, 1,2 elimination, but in this case it gives you, let's say we did it with zinc, it gives you the corresponding zinc salt. If you look at these two processes also from a conceptual point of view, in this case you are doing an overall reduction of your substrate and you oxidize your metal. Your metal goes from zinc to zinc halide and you are forming the alkene. So this is a so-called reductive elimination. While in the more common way here, when you eliminate HX, this is neither an oxidation nor a reduction on this base. So basically, you're oxidizing one atom, you're reducing the other one. So overall, there's no change in oxidation state. And so this is the more typical simple elimination where no redox process is taking place. So we are going to focus first on this, because this is the most common process. We will look a little bit on the second type of processes as well. So this is the process I would like to look at. We do a 1,2 elimination of HX from such a compound. And so typically, as we already said here, this requires a base, because what you do is you are eliminating a proton here, and this needs to be assisted by a base. But again, very typically or very related to this nucleophilic substitution reactions. Also, this can go in two different, as you will actually see that one of the pathways we split even in a third pathway. So we have actually three different types of reactions going. And so, again, similar to the SN, or very similar in this case to the SN1 reaction, there's also a E1 process, and that starts in the very same way like the SN1 reaction has been started, and that your leaving group is first going out of the molecule, resulting in such a carbocation. This is the same, very first same step as in an SN1 reaction. And now, so this is E1 or SN1. And now, rather than the nucleophile is combining with the carbocation, in this case, the base will deprotonate the system to form the product. So again, this is the elimination pathway, E1, and the SN1 pathway was where we had the nucleophile attacking here. So you see that this is very much related, and it is related in all aspects which we have seen from the SN1 reaction. So the kinetics are again that the rate determining step is the formation of the carbocation. And then, in the second step, the product is forming. So again, this here is the rate determining step. Since carbocations are being formed, we have the same aspects which we discussed on with the nucleophilic substitution at E1, never on primary halides. So if you form a primary carbocation, which I have actually drawn here, this is really a primary carbocation which I've drawn here. This is not going to take place by an E1 reaction because it is too unstable. And it's very well possible if you have secondary or tertiary atoms from which the leaving group is going. We will go back to some other factors which govern this in just a second, but let's look at the alternative reaction mechanism. This is the E2 elimination. And the alternative is that both groups are leaving simultaneously under the assistance of the base. So here you see that the base is part of the rate determining step here in this case as well. So the rate determining step involves substrate and base, and we have the typical profile which we had from the SN, which we had also in the SN2 reaction, that in the transition state the base is involved here and breaking should have, if I want to indicate a transition state here, so let me indicate the bond breaking. Here as well, there's no intermediate, and the reaction proceeds simply through a transition state, then to the products. So again, extremely related to the SN2 reaction, where simply you don't have a nucleophile, but you have a base which attacks at a different part of the molecule, namely abstracting a hydrogen or proton. And it's more or less also starting, or you can view a base, of course, also as a nucleophile. And if you look at this here, really the base is acting like a nucleophile on this proton, but then and then the elimination here takes takes place in this way. And so again, if you look at the this aspect here, the elimination according to the E2 mechanism is possible on all types of carbons. And here we see a distinction between E2 and SN2. Remember, the SN2 reaction was not possible on a tertiary carbon halide center because it was sterically too hindered. The steric hindrance is not there in a elimination reaction on this center here. No matter how sterically bulky this is, it is important that the base can reach the neighboring hydrogen here to abstract the proton. And since protons are on the outside of the molecule, this is not that's easily possible, and so the reaction does not really react to steric shielding a lot. And so therefore, we can go through the E2 mechanism by any type of substrate here on which the leaving center on which the leaving group is located. On an SN2 reaction, the SN2 reaction was really only possible on primary and secondary centers. So this is one distinction here. For the E1 reaction, this is completely analogous because the rate determining step is the same like in the SN1 reaction. This was completely analogous to the substitution. Okay. So let's look a little bit more at the mechanism of the E2 reaction And in principle, what would be conceivable is that such a elimination takes place either from a syn or an anti-conformation. So here in this case, I would like to suggest that one of the possibilities is that the base attacks anti to the leaving group here in order to form the new pi bond. And an alternative to discuss might be that a syn elimination could take place. In both cases, you see that the arrangement why we're discussing syn or anti is that when we eliminate these groups, we need to line up the p orbitals to form a new bond here. And so therefore, only a syn or an anti-elimination in principle makes sense, because then we orient already the atoms are already oriented in the right way to form the new pi bond here. And so in principle, this would be an equilibrium between these two conformations. And the question now is, what is going to happen? Or what is the more likely mechanism? And so what we need to find is probably we need to find some arguments for one or the other. Is there any suggestions from the audience on syn or anti-elimination? What is the magic sentence? There are steric and electronic reasons for everything, right? So, say something about sterics. The halogen, yeah?
Needs more place, and so the other side is more likely to react.
So what do you think is sterically better? It's the anti or it's the syn arrangement? And you can see, if you draw the structures, you can see that even from these simple structures, you probably have a pretty good case that in this case, sterics basically where the base is avoiding our leaving group. Let's say it's a bromine or an iodine. This is of course pretty big. And so I think immediately the steric argument would call that that the leaving group and the base would like to be group should be apart as far as possible. And so this would be an argument for the anti-elimination. Any other arguments here? If you analyze the conformation of these two compounds, it's the same compound, but the two different conformations which you get by rotating along this CC bond. What is the difference here? Or which conformation is the more likely one? Yeah?
I think the anti-conformation is also better of energetic reasons, because if you rotate them and they are syn, they need a little bit more energy. I think it's just 3 Q-joules per mole.
Yeah, okay, so let me combine this what you said. I think that everything is okay. You said this anti-conformation should be energetically better than the syn conformation. And really look at this. It's not so much a question here also of syn and anti. Okay, here we have the leaving group. But it's a question of a staggered conformation against an eclipse conformation, right? Here all the atoms are eclipsed, staggered, so they are not they are not aligned on each other, while here the two conformations are so let me remind you on this. This is a staggered conformation. German word gestaffelt. Where you have 120 degrees between the atoms, while here, in such a conformation, this is eclipsed. And you have steric repulsion between the groups, which are really on top of each other, have a dihedral angle of 0 degrees here. And so, in fact, if you look at a reaction or at a profile which looks like this, then here is really, the minimum is really the staggered conformation. And the maximum, the eclipsed conformations, really are more or less transition states, unless they are stabilized by some kind of intramolecular attraction. But other than that, the eclipsed conformation is a transition state between the staggered conformations. And so the argument was already said correctly that in the region of like 3 kcal per mole, an eclipse conformation is less stable than a staggered conformation. So that was the right range. But also, moreover, what is important to see here is that this is really a very short-lived conformation, because it's basically just on the transition to the next staggered conformation. And so also for this argument, one would say the anti-elimination occurs from a staggered conformation and is therefore also geometrically and energetically more favorable. And the third argument we can put forward for the anti-conformation is the following. If we are looking at the orbitals which we have in this molecule, then we have a sigma star CX orbital, which is aligned in this way away from the sigma CX orbital. Now, as the base is now taking off the proton, you see that a lone pair is developing here. And this lone pair is ideally suited to donate into this anti-binding orbital. And what it does is, by donating into the anti-binding orbital of the CX bond, is it weakens the CX bond. And so therefore this arrangement, from this arrangement, the moment the base starts pulling on the proton, there's donation, there's the electron negative charge is developing, and electron density is delocalized into the sigma bonding orbital, sigma star bonding orbital, and assists the leaving here. And this is something we would not have here, right? Because here in this case, we would have maybe some kind of repulsion of the bonds here, but we do not have a way to have the developing negative charge interact with a suitable orbital to assist and facilitate the leaving group. So the interaction of sigma CH with sigma star CX can only occur in the anti-conformation And so therefore, again, the anti-conformation is favored. So we have a lot of, or actually we have not a single argument found for syn type of elimination in these base driven processes. And so indeed, the overwhelming or the major driving force here is that such reactions occur from a anti-conformation. And this is sometimes very good to keep in mind, even when you do your PhD. Let me show you an example. Yeah, you have a question.
I'm sorry, I don't understand the last point. Why the H is going to CX?
Okay, so let me draw this here again. So the question was the last argument. As you pull off the proton, a negative charge is developing here on this carbon, right? Because you're taking away the proton. And so we are having basically a delta minus, let's say we're taking away the proton completely. We have a carb anion developing here. And this carb anion would like to be stabilized somehow. And the question is, how can it be stabilized? Since it has 2 electrons, it can only interact with an empty orbital. And if we have this anti-conformation, the anti-orbital from the sigma, from the CX bond, which is the sigma star CX orbital, is aligned to do this. And so therefore, we can have some delocalization of the developing negative charge into this orbital. All right, so let me draw this in an extreme way. So let's pretend, which is not going to happen, but let's pretend we are pulling off the proton altogether. I could write a mesomeric structure which looks like this, where I delocalize the bond in the negative charge to the next atom and are breaking the CX bond. And you know, this is exactly what basically the process of the elimination is. But this can only occur if the orbitals are aligned correctly. And they have to be aligned parallel. They cannot be aligned anti-parallel. And so therefore, this arrangement you have only in the anti-conformation, which then indeed exactly this process which I very tentatively are writing here as mesomeric structures as a stabilization, how the negative charge can be stabilized by the adjacent sigma CX bond. And then of course you know that this is exactly what is going to happen, that it's not only delocalized in a form of a mesomeric structure, but that it is really kicking out the X group and is doing the elimination. This can, as I say, this can only occur in the anti-conformation. It cannot occur in the syn conformation. And let me show you that sometimes it's good to remember these things. Even if you do already your PhD, and let me show you this. We were having this molecule which is a precursor, was very close to a natural product, which is an anti-cancer drug. And so what we wanted to accomplish is this elimination here. And the question is, how do you do this? So we wanted to have the elimination occurring to this position and not having an elimination occurring to this side, because this is how it is in the natural product. And we convinced ourselves that thermodynamically, we have to talk about this in a moment a little bit more, but thermodynamically this should be the elimination which should take place, because we are going to the tri-substituted alkene, and we did not want it to have this one. So this is tri-substituted. This is di-substituted. And the general rule is the more substituents you have around a double bond, the more stable it is. So the higher the substitution, the more stable your alkene. And so thermodynamically, this product should be favored. So the question is, what kind of reaction conditions should we have? And the one thing to realize is that you cannot make simply a better leaving group here and then try to treat this with a base and try an E2 elimination. So what you need to realize here and recognize is that if you want to eliminate to this side, an E2 elimination cannot work, because you have the wrong geometry between your potential leaving group, and we have to talk about leaving groups in a moment, and OH is not a good leaving group, but you can make better leaving groups out of OH. But any type of attempt on E2 reaction, no matter how thermodynamically stable or more favored this might be, the E2 mechanism calls for strict anti-arrangement, and we do not have this here. And in fact, we have anti-hydrogens over here. So any type of E2 type setup we do here has to fail and has to give us the wrong, and will give us the wrong, geometrical isomer, even though this might not be thermodynamically as favored. And so we might leave this on here for a moment, and then we can discuss how we were actually able to do this. But what was clear is that if we want to go to this thing, this should go by E1. And this is a E2 process, and most importantly, the E2 process will not lead to this product here. Okay, so the anti-arrangement is very strict for such kinds of base-induced elimination. Nevertheless, there are syn eliminations, and we will also cover this in a moment, but they are more specialized, and they do not follow this mechanism where an external base is inducing the elimination. So let's look at some examples, and there we can discuss then more of these factors. Let me see this. Okay. So let's briefly look at the question E1 versus E2. So typically, the E1 process requires a good leaving group. And a weak base. And why is this? The reason for this is that what you need to accomplish is that the leaving group should be so good that it leaves the molecule to form the carbocation without that the reaction that the elimination is occurring in the first step here. So this is the E1 step again. And the weak base here is also necessary then, because if you have a strong base and a good leaving group, then the base will immediately attack the proton here. And start a E2 reaction. So usually also good leaving group is important in both of the processes. But strong bases are favoring the E2 pathway. And so typically the setup for E1 processes, typical conditions are that you transform, that you do elimination starting from alcohols, and that you are not using basic but acidic conditions. And so here is again an important strategy. OH is a very bad leaving group, but you can protonate that leaving group, the hydroxyl group, and this way you're forming a very good leaving group, namely water, which is able to leave very easily to form the carbocation here. And then only in the second step, the deprotonation occurs from your base. Now again, very important, very often when you are formulating these mechanisms, because you know you need a base now, you would like to say, okay, now OH minus hydroxide is attacking here to finish the elimination. Keep in mind that under these conditions, there is no OH minus present. If you are an acidic pH, you have water and some kind of a proton and some kind of an acid, so you have H3O plus and water. So your strongest base in this scenario is water, but not OH minus, which then will complete the elimination here. And so in this case, forming this. And so indeed, going back to this question here, indeed what had to be done is that you would simply do the elimination under acidic conditions, favoring, simply the protonation favoring the leaving of the OH group to form the carbocation. And then, of course, from either side, the elimination could occur. And because this is thermodynamically driven, then the thermodynamically more stable product has been formed. And so these type of E1 type eliminations you typically also see with halides. It's the same idea. So also if you have halides again under acidic conditions, you can drive these reactions to an into an E1. Type of process by protonating your leaving group and making it a better leaving group. And then forming the product. And again, keep in mind here that also here again 2 types of products are possible. You can either form the internal double bond here, or you can do the proton abstraction can occur on the end here. And again, the higher substituted one is thermodynamically favored. And so under these type of E1 conditions, you generally have thermodynamic control and you form very often mixtures, but the thermodynamically more favored, more stable product will form. You have a little bit more control on these regioselectivity issues in an E2 type. Where do I have my examples? So let's look at the regioselectivity in comparison of a E2 reaction where you have a base and you are attempting therefore the elimination. Tertiary halide, there's no question of substitution here. Substitution cannot compete under these conditions. So here typically E2 conditions, But the products you can get is you always look for the adjacent carbon and see if it has hydrogens on there. So the products you can get here are twofold. You can either abstract this hydrogen. Let me put a small a on here and a small b. So this would be product A. And the alternative would be the abstraction of this proton to form the regioisomeric one. So again, thermodynamically favored. And this product is kinetically favored. Why is this? Why should this be kinetically favored here? And I'm missing a methyl group here, sorry. Yeah?
Because sterically, because the base might be big and it might be difficult to come to the tertial C and to abstract the H or the proton.
Okay, so interesting argument is being heard. So I asked, why is this kinetically favored? And one of the answers was, or the answer here, or one's argument was put forward, maybe the base cannot really reach here so closely, and it can more reach here. And indeed, that's a good argument, because this is sterically, of course, still more shielded than this. So it's easier to reach these type of protons. But I guess the even more important thing is, look how many of these type of protons we have here. We have 6. We have only 1. So either of these HBs it's abstracting will lead to this product. So it's kinetically, yes, it's sterically more shielded. So a reagent is more likely, or it's easier to assess this. But also we have a lot more hydrogens available. So statistically, it's also much easier. So HB is less shielded. And also statistically, simply on the number, statistically more available. And exactly what was already said on the shielding is now this gives you the possibility for differentiating between these two positions. So if you choose a base the deprotonated ethanol here, sodium, the sodium ethoxide, small base, and it can more or less reach each of these. And so what you observe is about a 3-to-1 ratio, again for the thermodynamically more favored one, despite the fact that we have much more hydrogens to abstract to reach the other product. And then indeed, if you use a sterically more hindered base, and this is a base you should also remember, because from the alcohol bases, this is being used very often. It's the alcoholate from T-butanol. So this base here is potassium tertiary butoxide, and so you see this very often abbreviated as KOBT, or you just write the formula like this. Sterically very hindered, very crowded base. And so in this case, although protons generally are on the outside, on the periphery of a molecule, in this case we still have a tertiary proton to abstract. And as the outcome is that you observe exactly the opposite. Yeah. So this is one way you can control the regiochemistry. I should also mention two names here, that if you form the higher substituted product, this has also a name. This is the so-called Zaitsev product, after a Russian chemist who worked a lot on these type of eliminations. And this is the so-called Hofmann product. And you will see in a moment why this is, because there's a way to even more favor these type of less substituted products. And that was named, and the way how to do this was named after its inventor, Hofmann. So very often you also talk about, if you form the higher substituted double bond, you say that you are doing a Zaitsev elimination or the Hofmann elimination to the less substituted double bond, or you call this the Zaitsev product and the Hofmann product. And so here we look simply at sterics. But equally important in how you can also influence regioselectivity is the leaving group. And I would like to show you this with one example. Where we have an alkyl iodide, and we compare this with an alkyl chloride. And ultimately we compare this with this ammonium salt, where we have as a leaving group trimethylamine here. If you compare this, you can see that the leaving groups from here to here become less good, or let me put it in the other way around. This way, better leaving groups here. So the carbon-iodine bond, as the weakest bond of all these three here, is very easily broken up. Carbon-chloride bond, much more stable bond. And then here the carbon-nitrogen bond is a very stable bond and even less good broken up. And so if you do now, in all three cases, the elimination chemistry, there are two products which you could obtain. And again, it's the formation abstraction through this side to form the higher double bond, and as an alternative to do the abstraction from here to form the less substituted double bond. And if you're going to do this, and you're using ethanol, the ethoxide as the base, what you're getting is about a 5-to-1 ratio in the case your leaving group is iodide. If you do this with chloride, you're pretty much getting a 1-to-1 ratio here. I should have, excuse me, there's a little bit different base here. It's the T-butoxide base. So let me stick here with the real number. So if you use T-butoxide sterically hindered base, you are still forming with the iodide the thermodynamically more stable one. With the chloride, you are getting a 1-to-1 mixture here. And with the trimethylamine leaving group, so here we have chloride, iodide, triethylamine as the leaving group. And here as the base was used hydroxide. This is the number I have, is that you are forming basically exclusively the less substituted double bond here. So although we have here some steric differences in the base, interestingly enough, with the smallest base which was used in this case, because in these type of eliminations you will always use hydroxide, the probably most unexpected product is obtaining based on steric arguments, right? Because you're forming you have a small base, but you're still forming the thermodynamically less favored product. And you can see here in this case the same base is being used. And apparently, depending on the leaving group, the ratio of these two things are changing. And all three are E2 eliminations. So we have the classical E2 setup. But the question is, why is this? What is going on here? And we already said that one of the differences is the leaving group here. And the trimethylamine leaving group is it's not a very good leaving group here. And the reason it is argued that if you have not a very good leaving group, that preferentially the less substituted double bond is formed, is as follows. If you have the base, if the base is pulling on your proton, usually the normal SN, and if you have a good leaving group, as this is being pulled off, this is being pulled off as well, and you're forming the double bond, and so the product is driven by thermodynamics of your product. If this is a bad leaving group, then what you're in extreme, as an extreme representation, what you're forming is that you're having a transition state where the base has pulled off the proton, but the leaving group is still sitting pretty tightly on your carbon. And so here in the transition state, this transition state has a considerable developing of negative charge here on this carbon without that the reaction is continuing. And so you're forming a negative charge here, or alternatively, if the base pulls off this proton, then the negative charge is developing here. And so the worse the leaving group is, the more unsymmetric the transition state goes. And as I say, the extreme you could think about is that you're really forming a carbanion first. And in this case, a negative charge is better stabilized on what? On the higher substituted or on the less substituted carbon? Yeah? On the less. Why is this?
Because the alkals putting a plus I effect.
Yeah. Right, we always said alkyl groups are donors. We talked about hyperconjugation. So because of the donor ability of the alkyl groups, carbocations, the higher substituted they are, the more stable they are. Anions is exactly the opposite. The anions do not benefit from donation, so the less substituted a carb anion is, the more stable it is. And so this way, if you are in a situation like this, where basically the base is pulling off the proton much more than at the same time the leaving group and is going out of the molecule. So the transition state has carb anion character, and this is better stabilized on the less substituted carbon, which then takes the negative charge. And we see this here then very dramatically. As you can see, is based on the leaving group, you are able to switch over the Rigo selectivity from 5-to-1 in one direction to 20-to-1 in the other direction. And so this type of process is the so-called Hofmann elimination. And you always see this with amine groups. And so typically, the way such reactions are initiated is that you have a dimethylamine which you might generate from the reaction of by nucleophilic substitution of your halide here. We have talked about the problematic of doing direct nucleophilic substitutions with amines on halides. And then typically what is being carried out is that a further alkylation occurs. You set up if you treat such a tertiary amine with methyl iodide, you will form the ammonium salt here. And then typically with a base hydroxide, is sufficient you do the elimination, and this is the so-called Hofmann elimination. Basically, dimethylamine followed by alkylation with methyl iodide is utilized as a leaving group here. Important also to realize, instead of methyl iodide, could I also use something like ethyl iodide? Does it matter what kind of alkyl halide I use here? What do you think? Ethyl iodide is doing the same type of reaction. No, you have to use methyl iodide. You have to utilize the trimethylamine group as a leaving group. If you have ethyl or any higher type of alkyl chain, you also create better. You also have better hydrogens on your amino group, right? So let me just draw this here. So on your ammonium salt, on your leaving group, please realize that no elimination can take place to this side because you have methyl groups here and no other beta hydrogens here. If you would have an ethyl group here, you could also eliminate to this side. So you need to set it up like this. You need to generate the trimethylammoniums group here in order to set this up. And also it needs to be the trimethylammonium group, also very classical. The question, can I do in any type of way eliminations directly from hydroxyl groups? And the hydroxyl group, no matter what kind of base you start here, the hydroxyl group is a very bad leaving group. And so typically eliminations of this type do not take place. You always have to go, in this case, if you want to start directly from an alcohol, you have to go through the acid catalyzed type process and eliminate water this way. However, and that's the last thing I would like to show you today, and this brings us into the third mechanism which exists in elimination type reactions. If you have very acidic protons, so now we are getting close to this idea also which we had in this Hofmann reaction, but this type with an even worse leaving group, hydroxide. If you have very acidic protons, like a proton next to a carbonyl group where you can form enolates, then what is happening very rapidly is that you deprotonate on this position. This is an equilibrium, but you start forming such an enolate here, such a carbanion. And if this is sufficiently stable, it sits around, and at some point, and again in a rate determining step, it will actually kick out this very bad leaving group. So here this would be the rate determining step. In order to eliminate this. And this is the so-called E1CB elimination. It's an E1 reaction because from the kinetic, because this is fast, so the base plays no role into this. This equilibrium is fast and only determining from the substrate. The elimination is rate determining, so it's a first order kinetics. And the CB here stands for carbanion And the carbanion, simply because you are forming a carbanion here first, and then elimination takes place here. So the requirements for the E1CB reaction is that your anion has to be stable, stable carbanion, and bad leaving group. And so these two things are the typical ingredients under which such kind of elimination can take place. If you have a good leaving group, like a halide here, of course, such eliminations with base take place, but then it's a normal E2 elimination because the leaving group leaves immediately once the bases starting pulling off the proton. But if the leaving group is bad, but on the other hand, you have to have the stable carbanion so that you can build up a sufficient concentration here that it's stable enough to do this. In this case here, no matter if you have a very strong base here, this carbanion is so unstable that the equilibrium with any type of strong base is all the way on this side. And so therefore, eliminations do not take place unless you are able to stabilize the carbanion here. Okay, so much for now. Tutorial starts in 15 minutes. Also was last Wednesday. Whoever ran away, there was a tutorial last Wednesday. I heard there were only 15 people here. Okay, but again, no. David Diaz only said he is not doing the tutorial. That is two different things. The one thing is he doing the tutorial? The other thing is there a tutorial? Okay, so 12 o'clock here with me.